Welcome back everyone. In this lecture, we're diving into the critical role of physical transport processes in environmental biotechnology. By the end of this lecture, you'll understand how these processes shape the design and evaluation of biotechnological systems, from lab-scale experiments to full-scale wastewater treatment plants. As we have discussed in previous lectures, environmental biotechnology focuses on designing processes that selectively enrich desired bacteria to perform specific conversions, like breaking down pollutants. To achieve this, we need to understand two key aspects of bacteria: the stoichiometry, the balance of substrates and products in their reactions, and the kinetics, the rate at which these conversions occur, like the maximum growth or conversion rates. Here's the key: these bacterial processes are scale independent. A bacterium behaves the same, whether it's in a test tube, a bioreactor, or the ocean. What does change with scale is the reactor environment, driven by physical transport processes. These processes, such as the movement of substrates or oxygen, differ significantly between a 1 liter lab reactor and a 1000 cubic meter full-scale reactor. Understanding the physical transport processes allows us to translate lab results to real-world applications and troubleshoot full-scale systems by focusing on what's happening at the bacterial level. So what are physical transport processes? They involve the movement of matter, heat, or momentum through a medium driven by forces like concentration gradients or external mixing. In environmental biotechnology, we are primarily concerned with matter transport. Think wastewater entering a bioreactor, bacteria growing and mixing within the reactor, and treated wastewater and producing biomass exiting. The physical transport processes connect the microenvironment, the bioreactor as a whole, to the microenvironment, the immediate surroundings of a bacterium, around 1 micrometer in scale. For example, in wastewater treatment, bacteria rely on substrates like oxygen or pollutants delivered through transport processes. Understanding this transport ensures we can control the conditions bacteria experience, whether in a laboratory or a full-scale facility. Let's explore a concrete example: oxygen transport in aerobic processes, like those used in wastewater treatment. Oxygen starts in gas bubbles provided by blowing air in the reactor. The oxygen moves through several steps. First, the gas-liquid transport. Oxygen dissolves from the gas bubble into the liquid, diffusing through a thin stagnant film where its concentration drops. Then there is mixing in the reactor. The reactor mixing distributes the oxygen in the liquid phase. From the liquid phase, there is diffusion to the biomass. Oxygen reaches bacterial flocs or biofilms, passing through another stagnant liquid layer. Diffusion and conversion are happening inside the floc. Oxygen diffuses while being consumed by bacteria. Each step, the gas-liquid exchange, the mixing, the diffusion, and within the biomass aggregates, shapes the oxygen concentration the bacteria finally experience. If the microenvironment in a full-scale reactor matches the microenvironment of the laboratory conditions, bacteria will behave consistent. If not, difference in transport processes are often the culprit for the difference. This is why understanding these steps is critical for scaling up processes effectively. Let's look at nitrification, where ammonia is converted to nitrate using oxygen and CO2. The stoichiometry tells us which compounds enter or leave via the liquid phase, like ammonia and nitrate, and which interact with the gas phase, like oxygen and CO2. Here's where scale matters. In a 20 centimeter lab reactor, treating ammonium-rich wastewater, oxygen is often the limiting factor due to aeration constraints. But in a 6-meter tall industrial reactor, CO2 becomes the limiting factor because air contains far less CO2 than oxygen. These shifts require us to rethink gas supply strategies at full scale, perhaps adding supplemental CO2 to maintain optimal conditions. This example shows how transport processes and scale influence process efficiency. Now let's break down the key transport processes. Starting with advection, the bulk movement of liquid. This includes wastewater flowing into and out of the reactor and the internal circulation driven by mixing or aeration in large bioreactor, like those for wastewater treatment. Mixing isn't perfectly uniform, as this image shows. Liquid velocities vary across the reactor, creating zones with different conditions. Bacteria in each zone experience unique substrate availability, so understanding advection helps us predict and optimize bacterial performance. Next is diffusion. Critical when bacteria are immobilized in biofilms or flocks, as is common in wastewater treatment for biomass retention. Substrates, like oxygen, reach these bacteria only through diffusion, driven by concentration gradients. In this image, you see within a red line a biofilm with a stagnant liquid layer outside of it. The oxygen concentration drops across the layer and further inside the biofilm where it's consumed. This creates a steep gradient, often leaving deeper layers oxygen-starved. Understanding diffusion helps us design systems to ensure substrates reach bacteria effectively, avoiding limitations that could slow conversions. Mass transfer, like oxygen moving from gas to liquid to biomass, is often described by a rate equation. A rate, expressed in grams of oxygen per cubic meter per hour transferred, is depending on the KLA, or the mass transfer coefficient. C star is the equilibrium concentration and C is the actual concentration in the liquid. The oxygen concentration drops at each step: gas bubble, liquid, biofilm particle, due to transfer and consumption. The trick to optimizing a process is identifying the rate limiting step. Is it the gas-liquid transfer, the mixing in the reactor, or the diffusion into the biomass, or even the conversion inside the flock? Pinpointing the limiting step tells us where to focus for improvements, like increasing aeration or reducing particle size. A critical concept in transport processes is specific surface area. The surface area per unit volume of a reactor, for instance, the gas bubbles or biomass particles. The specific surface area is inversely proportional to the diameter. Half the diameter and you double the surface area. This matters because more surface areas means faster mass transfer, whether it's oxygen from bubbles or substrates to the bacterial flocks. In design, we can optimize specific surface area by adjusting bubble or particle sizes to enhance process efficiency. To wrap up, physical transport processes are the backbone of environmental biotechnology. They govern how substrates move into, through, and out of bioreactors, shape the microenvironment bacteria experience, and thereby the type of bacteria enriched. Key processes include advection, the bulk liquid movement like inflow, outflow, and mixing; diffusion, substrate movement to immobilize bacteria in biofilms and flocks; mass transfer, gas to liquid and liquid to biomass transfer, often limited by specific surface area; conversion, biochemical, the reactions inside the bacteria tied to stoichiometry and kinetics. When evaluating or designing a process, always consider how substrates enter and leave via advection or gas-liquid transfer, how they are mixed and delivered to the bacteria, for instance via diffusion, and which step limits the process performance, and how scale impacts this. By mastering these concepts, you can bridge the gap between laboratory experiments and real-world systems. In the rest of this course, we'll explore practical examples of these principles. Thank you for your attention, and I'll see you in the next lecture.